Goedemiddag. Yeah. Great. Okay, welcome to the 10th lecture on multibody dynamics. Is the audio thing on? It says on. Oh, mute. Okay, this should be better. So the topic for today is rotation matrices and Euler angles. Maybe a very short interlude about homework. We have had some trouble with grading homework 6 and 7. Some things about the rules and guidelines were not clear. People said, hey, I work together with Jan. And Jan said, hey, I work together with Kees. And then, yeah, you get that work. And then you know, yeah, what did Jan do and what did Kees do? That was totally unclear. So since we are already so far in the course, we really expect that you know that if you use work by others, just mention it. Yeah? Be clear, crisp and clear about that. It doesn't inflict your grading. But say working together is, I have no clue who did what. So our rule base is then we divide the grade by the number of people you work together with. Yeah, I have to give an incentive to make clear to you, please write down what is yours and what is others. You don't do that for me, you do it for yourself. Homework is a learning curve. It's a feedback, it's a learning moment. Okay, that having said, to the fun business, topic of today, rotation matrices, Euler angles and angular velocities. Yeah, in a three-dimensional space. In a two-dimensional space it was all super clear. There was one rotation, but in 3D it's like, ooh, it's very spooky. Very strange things suddenly happen in three-dimensional kinematics mainly. But before we do that, of course, we start with the quiz, Kahoot, huh? Yeah, okay. Oh, that was not smart. Let me get back. That was not so smart. Yeah, okay. Am I back? Yeah. Kahoot. Today's quiz is actually not so hard. I mean, temperature is high. Let me see. Is it 10? Yeah, I guess it is. 3 hours ago. Bam, bam. Okay, well, when people start dropping out, we should start, right? This is about mass moments of inertia. So it's an object which is familiar to most of you. Of course, you can take out your calculator, but actually it's not necessary here, I guess. Yeah, discuss, please. Convince your neighbor that you are correct and he's wrong. You're right, he's wrong. Of course, you can calculate if you want to. I have mixed feelings when I look at the results. Maybe like Daddy is a bit disappointed, something like that. I mean, if we look at the media, then it's clear that about the a lot of numbers and so on, but if you look at the answers, the only thing you have to order is 3 numbers, the smallest, the middle one, and the largest. So without even calculating, you just look at the object and you think, well, the smallest I can identify easily, right? That should be around the x-axis. So the smallest number should be there. Then the largest one, well, that is of course with the largest projected plate, so that's the z-axis. So if you know the smallest and the largest, and the other one is already defined, and that's the answer. Okay, next one. Wahed, you missed your grade. Yeah, this is about the Euler equations of a rigid body. This is not so hard, right? Yeah. Well, all the Newton equations are linear in the mass. Force is mass times acceleration. If you increase the mass, if you multiply it by 2, apparently then all the forces will be multiplied by 2. Yeah? There's no other way I can think of this. It's linear in the mass, you could say. Krakaka, are you here? Yeah, okay, good work. Okay, this is about really calculating numbers with the Euler equation. And I advise to use scrap paper. Just scribble, and it's not so hard, but you just need some scribbling. This is what we call a learning moment, right? Yeah. Maybe the time was not enough. That could be the case. So maybe I'm going to re-ask the question again next week. Who knows? Since there are so many people in the wrong and so few in the right, so apparently the wrong answer are these numbers. Now it's not about the numbers, of course, it's just these numbers. 0, 0, 0 almost can't be true, right? I mean, but okay, 90 still think. So what is the whole problem? We have an angular velocity and we have a nice diagonal mass moment of inertia. So the momentum, the angular momentum, which is mass moment of inertia times angular speed, is just this vector multiplied by this diagonal matrix. So we have an angular momentum which is something like 0, 6 and 8, something like that. Then we have to take the cross product of the omega with that angular momentum, that are these convective terms, and some vector will come out of that, some numbers. Since there is no torque, we have to then divide that by the mass moment of inertia and put a minus sign in front of that, and that is then the angular acceleration. It's simply applying Euler's equation to this very simplified problem. Okay, next question. Stable torque-free rotation is possible about, we have again that famous object, and it's clearly indicated about the axis what is the largest, the middle one and the smallest. And I'm asking about stable torque-free rotation. Yeah, it's a bit confusing, but of course in multiple choice there can be more than one answer right. I mean, that is sort of the fun of multiple choice, or to make it not too easy. So yeah, correct. It's the intermediate axis is unstable, or in other words, the largest and the smallest mass moment of inertia axis are the stable ones. Very good. Okay, we are already at the last question. Because in 3D, so this is about the topic of today. You should know what that is, right? With your Latin background. Yeah. Well, maybe you can translate the omne trium perfectum for the audience.
All the three groups are perfect.
Yeah, yeah, all things which come in 3 are perfect. So you can think about the trias politicus, or there are various ways to interpret that, or the 3 Euler angles, or it was usually a term which was used in Schauspiel, theater, where they say, well, if you have a play with 2 actors, I'll finish this session. If you have a play with 2 actors, then it's not fun. But if there are 3 actors in a play, then you have real dynamics in the play. So therefore you need 3 people. Okay, obviously it's not the correct answer, although 5 people liked it apparently. Yeah, you would think, and that's 58 out of the number we have, 100 and something. So the majority says we have 3 orthogonal base vectors. And it would be tempting to say so. But let me disprove this immediately by going back to a 2-dimensional world. How many base vectors do we have? 2. Ergo, there are 2 rotations. Forward and backward? No. So your whole scheme of thinking, oh, I have 3 base vectors, so therefore I have 3 rotations, forget it. From now on, that's not true. Never ever. Because in a 2-dimensional world you have 2 base vectors, and you don't have 2 rotations. Rotations is a bit more complex, and that's the topic of today. So let me see for the whole score, yeah, get the results, save the results. Please give feedback. I always like feedback. I give you feedback, you give me feedback. Okay, that's done. Show the feedback. Yeah, good learning curve. That was nice. Okay. Then the next step is this one. And we make it full screen. Before I do that, I'll check Everything is running, that's good. Okay, yeah. So topic of today, rotation matrices. Now let's go back to the Euler equation. So Euler equation in 3D, of course, was simply that we had the sum of the torques, and we do it about the mass moment of inertia, equals the center of about the center of mass, sorry, mass moment of inertia about the center of mass times the angular accelerations plus omega cross product with I omega. And of course this quantity is usually has a name, and we call that angular momentum. We also have a symbol for that, angular momentum. We usually call it H is I omega. And it's like a vector. So you have a vector which is like angular speed, and then if you multiply it with the mass moment of inertia, you have a quantity called angular momentum, which you can compare to linear momentum, mass times speed. And in the old days they always thought that there was energy, Huygens, etc., but we now know that's just momentum. And forces are changes in momenta. So if you look at linear forces, that's the change of the linear momentum. And if we look at angular forces, which we call torques or moments, then that's the change in the angular momentum. And the change in angular momentum can be in two ways, because the body is rotating, that's this contribution. And the other change is, of course, that the angular speed is changing. So that's the change in the angular momentum. It's a nice concept. It's not part of the lectures now. It's sort of fun, but I choose to not do it. Just basic order mechanics. Now, if you look at these equations, where are the parameters that describe the orientation of the body? Can anybody indicate where they are? Yeah. Yes, exactly. So in the mass moment of inertia is sort of hidden the orientation of the body. Now these equations I've written down with respect to an inertial frame. You can also transform all these equations and formulate them also in a body fixed frame. And if I do that, and I use a prime for the body fixed frame, I get the following set of equations. And the prime just indicates a body fixed frame. We have a nicer notation in the book, but this is just a quick shorthand way to say, so prime is body fixed. Yeah, coordinates, I will say. Now again, let's look at the Euler equation, but now in the body fixed coordinates. Where is the orientation of the body? I don't have to repeat the answers because all answers are incorrect. I don't remember what. Somebody said omega and you said center of mass. The answer is it's not there. Of course, in the omega is essentially a deeper thing, like yes, but the omega is something with change in orientation. So it must be somewhere there, hidden, change in orientation is there, but the orientation itself is not there. So that puts us to the next question. What is orientation? How do we describe orientation? Position is easy. You say, oh, we have an XYZ coordinate system, and you put it somewhere in space. You have 3 coordinates. Or in other words, from the 2D to the 3D is just adding one coordinate, the Z coordinate, and you're in business. But now for the orientation, the only orientation we know up till now in the 2-dimensional world is one angle. And that angle is, of course, the rotation about the Z-axis. If we use the XY as the plane, then the Z-axis is the orientation of that axis is fixed. So the axis of rotation is fixed, and the rotation can only be about this fixed Z-axis. So that is the orientation in 2D. Now in 3D, it's more complex, the orientation, and you would be tempted to say, oh yeah, there are 3 axes, so you have 3 rotations, but now you know, of course, from the quiz that's not right. So how does it work then? For that we just have to look at a rigid body, so we just draw a rigid body with respect to some inertial frame. So we have this inertial frame, which we nicely now denote by this curly n for inertia frame, with the x, y, and z coordinates. And then we have some rigid body, and here we have a CM, and then glued to the body, fixed in the body, is a coordinate system, x prime, y prime, and z prime. And we say this coordinate system is with this curly b, that's the body fixed coordinate system. Actually, the arrows I draw are base vectors. So the x, y, z is in fact e x, and this is the vector e y, and this is the base vector e z. And likewise, this one is a base vector e x prime. This is a base vector e y prime, and this is a base vector e z prime. So with base vectors, we usually donate them with a underscore for the vector or a bold in the book, and a hat for that. It's a unit vector, it's a base vector. Now looking at this picture, you can imagine, oh yeah, that is the way how I describe the orientation. If I know how those 3 base vectors, and I'll use my hand for that, if I know with respect to my inertial frame, and for now I play the inertial frame, if I follow what these axes are doing, then I know what the orientation of the body is. Because these are glued to the body. So that is probably the whole trick. Now, the purpose, of course, for knowing the orientation is that you want to keep track of all the points in the body. So let's identify one point, and we take this specific point P, and we want to know, as a function of this orientation, where we still have no clue what that actually is, but we want to be able to track where is point P in our inertial world, as a function of this orientation. Therefore, we make a vector P, and I still say, I can write, well, the vector P, it's not algebraic components. I do not say in which coordinate system yet. I say, well, there is a vector P, and I use as the origin this center of mass. Of course, I should also add for the absolute position the translation, but translation is no topic for today. So we don't talk about translation, so let's assume that everything is in the origin, or that the center of mass is at the origin, is at 0, 0, 0. Forget about translation. That's boring. Boring, exactly. So only look at rotation. Now, how do we identify point P? So you can say, well, it's a vector, but eventually, if you want to calculate, you have to go back to algebraic components. You have to express that vector in a frame. And we have 2 frames, inertial frame, body fixed frame. Now, the vector P, I can write it, for instance, as a function of the inertial frame. So I can write it with these base vectors. We have EX base vector, we have the EY base vector, and we have the EZ base vector. And just as a linear combination of these 3 vectors, I can write it. And then these are the components. We call it PX, PY, and PZ. So this is the vector, and then these 3 numbers are what we say are the algebraic components of the vector. And we are tempted actually to write those 3 in a vector form, because in MATLAB we have to calculate, so eventually we need numbers, and the numbers we put in MATLAB are always these numbers. So in our head we always have to remember what the reference frame is we are using. Or you do a notation. Well, likewise, like with reference to the inertial frame, I can also say, but for the same amount, I can write down the vector in components with respect to this body fixed frame, with the prime, E prime, and then EZ prime. So I can write PX prime, PY prime, and PZ prime. So those are then those components, the px prime in the body fixed frame. Now there is a big advantage for this pi prime, yeah, because for a rigid body they are constant, and that is a beauty, yeah, constant for rigid body. And what do we mean by that? Well, your nose, I always say your nose is in the middle and in front of your head. And if you turn your head, luckily your nose will stay in the middle and in front of your head. Well, a little bit. It can move a little bit, but the same with your right ear. If you tilt your head, your ear will always remain on the right-hand side, approximately in the middle. And if it doesn't, then you're not a rigid body, right? That's how those. So for a rigid body, these pi primes, px prime, py prime, they are constant things. Now, what we like to know is how do we transform one into the other? Now, first of all, we have to find out how do we get components. So if we have a vector, how do we get the components of a vector? Well, if you look at this expression, and if I take, for instance, the dot product of this p vector with ex, then the outcome is the one number. Px itself, that component px. And why only px? Well, because all the other products, so ei dot product with j is 1 if I equals j, and it's 0 if I is not equal to j. So these base vectors are what we say are orthogonal. Orthogonal base vectors. Orthogonal base vectors. Okay, so now we have a trick to get a component out of a vector. So we can write, don't tilt. So we can write that we get the, no underscore. The pi we get by taking the ei with the dot product with the vector p. Still, that doesn't help us much, but now I'm going to use a trick, because for the presentation of p, I'm now going to use the presentation within the body fixed frame. So I'm going to write it as, okay, ei dot product with, and then I substitute this whole stuff. Copy. This. Yep. So let's close the bracket. So if I then do this multiplication, then suddenly I find the relation between the ones in the inertial frame versus the one in the body fixed frame. And the only thing I have to do is take all these dot products. And, well, this is of course for I is x, y, z. So in total these are 3 equations, and then here we have 3 base vectors. So in the end I end up with 9 by 3 by 3, 9 of these dot products. And if you do it properly, you get the following expression: px, py, pz equals. Okay, so the first should be the ex dot product with the ex prime, and then I get on the right hand side px prime, right? So that's the first. And the second one is this one. Then I get again the ex dot product, and make the dot real dot, with the ei prime. And then the last one is of course ex dot product ez prime. And we have py pz. And of course we continue. If you now see how this works, you can just fill out the whole matrix without thinking, because the next one should be, of course, be an ei hat. Ei hat. And the last one should be an ez hat. Ez, and all dot products. Oops, that's not a z. All dot products, and the dot products are with, and then we just have to repeat the ex prime dot product e y prime dot product e z prime, and here e x prime e y prime. And I write it out on purpose so you really know, oh yeah, I have all these different 9 dot products. There's also, of course, a shorthand notation for this with our nice index notation. You could write pi equals ei dot product ij prime and then pj prime. And then I and j run over x, y, and z. This matrix, this mapping, oh, where's the bracket? This mapping, this is exactly what we were seeking. So if you know where your nose is in your head, and you know how your head is oriented in the world, you know where your nose is in the world. Or in other words, we had this nice notation in the book. How did that go? With B, superscript and subscript. So actually this pi is a vector expressed in the worldly frame, and then this vector is a vector expressed in the body fixed frame, and then we have a rotation matrix from B to N. So this was the nice notation which we had in the book. So body fixed, algebraic components, rotation matrix, and this one. So apparently, I'm going to drop all these indices because it's a bit too much now for me to write. But in the book, you see it all clear and clear. I will use P is R times P prime. For now, that is clear. With the prime, I mean the X, Y, Z in the body, and with the other ones are in the world, and the R is the rotation matrix. Okay, now, so apparently orientation is described by this matrix. So you could say, or again in components, Pi is Rij times this Pj prime, J being X, Y, Z, 3 steps. And this we call the rotation matrix. Okay, how many components does the rotation matrix have? How many entries? 9, yeah. So we have 9 entries in R, meaning that for a rotation matrix, for a rotation in space, we need 9 numbers. Right? Sounds a bit much. 9 numbers. Okay, let's put that on hold for now because I'm not so happy with the 9 numbers. How do we find the inverse relation? So the inverse being P prime is R minus 1 times P. Just by taking the inverse of the matrix, there would be a way, but there is of course another way. We just take our initial method like above here, right? And we did just flip around some of the i's and j's and the primes, and then we're sort of in business. So let's copy this part. And do I have everything? I hope so. Oh. Can always augment it. Oh, how do I? Oh, that doesn't work. Go back. That was a bad plan. Oops. That was a bad plan. Yeah, keep it here. Yeah. Smaller, 100. Yeah. Okay, we'll have to rewrite it. It's not so easy. Okay, so the thing is we want to know the components in the body fixed frame. So we want to know Pi prime is, well, we've learned the rule how to do that. You take just this base vector, Ei prime, and you just multiply that with the vector. And how do we do that? And then for the vector we take the other representation. So with a prime, of course, sorry. And then for that one we just take p x e x plus py ey plus pz. Easy, in a global reference frame. Or in other words, you have your pi prime is your ei prime dot product eij times this pj. Now this looks a lot like the other expression we had. The only thing which changed is the I and the j, yeah. So the I and the j is apparently changed. So the conclusion from this is that the inverse of this matrix is apparently the rji. Yeah? It's the or in other words, it's the transpose of our matrix. And that is a very interesting quantity. So we have a matrix where we say, well, if you need the inverse, you just transpose the thing and you get the inverse. And that's a very special thing. We call that matrix. So R is a orthogonal matrix. And actually this statement that the inverse is the transpose, you can also rephrase that by saying, well, if the inverse is the transpose, then apparently the R times the inverse is the identity, or in other words, the rotation matrix times the transpose of the rotation matrix is the identity. So those are the conditions which we have to fulfill if we make a rotation matrix. So you cannot say, oh, I have a matrix with 9 entries. There are apparently constraints on the entries. So those are constraints on R. Now, how many of these constraints are this? How many equations is this? Well, the identity matrix is 1, 1, 1. That's already 3. Then 0, 0, 0. So then we have 6. And here we also have 0, 0, 0. So in total, we have 9 conditions, right, on R. And how many entries do we have in R? We have 9 entries in R, right? So how many different rotation matrices are there? If we have 9 variables and 9 equations, how many solutions are there? 1, yeah, if it's linear equations, right? So now you have a feeling something must be wrong. I mean, I have too many conditions. I sort of freeze the whole matrix to, oh, we only have this one matrix for you. I'm sorry, we have no other matrices. So that can't be true. Well, if you look at these equations, of course, the statement, the off-diagonal terms, this one, is exactly the same as this one. Or in other words, if you do R transpose and you transpose that, then the result is, well, double transpose is again the matrix. And so the thing is symmetric. So the number of conditions you have is symmetric. These are symmetric conditions, so meaning I only have 3 diagonal plus 3 off diagonal, so I have 6 conditions. The only thing I can count is this one, this one, this one, this one, this one, this one, and the rest is symmetric. Yeah? So I have 6 conditions. So with 9 parameters, with 9 entries and 6 conditions, that leaves me 9 entries minus 6 conditions is 3, yeah, you could say degrees of freedom for the rotation matrix. Clear, huh? So 3 rotations, and then you say, yeah, I told you so, it were the 3 x's. Well, people do say that, yeah, I told you so. Well, let's do a quick calculation in the 2-dimensional world. So in 2D, how does it work? There we have 4 entries, right? And then the R transpose is the identity matrix is a 1, 1, 0. So that's 3 conditions. So 4 minus 3 is 1 degree of freedom in the rotation matrix. Well, that fits. What do we do in the two-dimensional world? We just take one angle, the angle about the z-axis. Okay, so two-dimensional world we understand. So let's make a table. So this is the dimensions and then the number of rotations. So one-dimensional world, how many rotations do we have there? There is no rotation, right? So yeah, maybe you do like this. No idea. I don't know what a rigid object in a one-dimensional world is, so there's no dimension. So two-dimensional world, we had 1 rotation, right? Three-dimensional world, we had 3 rotations. Four-dimensional world, we have 6. Why not 4? 4 axes, 4 rotations? Apparently not, 6. Where does 6 come from? Well, you have in this 4-dimensional world, you have 16 entries, right? So 4 times 4 is 16. And then these conditions, you can build a nice formula, but I always have trouble with that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 conditions. Ergo, with a minus, then you have apparently 6 rotations. Now, I will be frank with you. I don't know what a rigid object in a 4-dimensional world is. I have no clue what it is. You can say, if you think of a 4-dimensional world, for instance, as time and space, then time is also a coordinate. And then a rigid object in a 4-dimensional space is that time and dimension are interchangeable, apparently. I have no clue how that works, but it's mathematics. It's how it works. We call it an SO4 or an SO3 in mathematical terms, but to be frank, I don't understand that whole lingo, so let's forget about that. Such a rotation matrix is an orthogonal matrix, and in any dimensional space it has the effect that it doesn't change the length, or the eigenvalues of such a matrix are always plus or minus 1. So and that is the concept, of course, of this rigid body, that if you measure along a distance, and if you measure the distance from my nose to my ear, and I tilt my head, then that distance is invariant. So the meaning, that is the meaning of the eigenvalues being plus or minus 1. And minus is actually a mirroring, and 1 is a rotation, but those are not so interesting details. Now, finally, to maybe understand a little bit where the 1, 3, and 6 come from. What is rotation? Well, rotation is something which happens in a plane, and a plane is, and it happens to rotation about a vector which is perpendicular to that plane. And if you think in that realm, then you can think, okay, in a two-dimensional world, I have 2 base vectors. And with the 2 base vectors, I can build a plane, and perpendicular to that one, I have this rotation. So yeah, crystal clear that there's 1 rotation. Now I go to a 3-dimensional world. I have 3 axes. How many different planes can I build? Well, I take the first axis and the second one, and then I have a plane. And then I take the second and the third, and then I have a plane. And then I take the first and the third, and I have a plane. And those are all the combinations you can make. There are no other combinations. So with those 3 base vectors, you can make those 3 combinations. And that's it. Those are the 3 rotations. But they have to do with the combination of these axes. And the same with a 4-dimensional world. Then how many different planes can you make? Well, you take the first base vector, and then 1 plane, 2 plane, 3 plane. Then the second base vector. Where was I? 1, 2, 3, 4, 5, 6. Yeah, 1, 2, 3, 4, 5, 6. So in total 6 of these planes. And that is in my humble idea the way to think about rotations. Now luckily we do not go to a 4-dimensional world, we just stay in our 3-dimensional world where we're going to drink a 3-dimensional cup of coffee, and after the break we're going to talk a little bit more about those 3-dimensional rotation matrices.